but we have unusually famous people also speaking today. And there will be a talk by Anders Hansen later. But before that, we will have Evelyne Hubert, who's going to talk to us about symmetry preserving interpolation. Please.
All right. Well, thank you. Thank you for attending, inviting me to this program. So what I will speak about was announced just now. So it's kind of ever since my postdoc at MSRI, where I met some of you, and I discussed extensively with Liz. Symmetries in algebraic computation has been a major part of my research. So starting with the moving frame and some differential equation, and now some more purely algebraic problems. And so the one I want to speak about today is interpolation. And I will be presenting the PhD work of Eric Rodriguez, who will be on the postdoc market next year, so advertising. So interpolation, the plan of my talk will be, I'm going to spend a lot about definition and not especially my own work, but you all know interpolation. It's going to probably hit things you already know very well, but I will nonetheless want to emphasize this least interpolation space that was defined by De Boer and Ron, and that I will expand on with a symmetry perspective about that. And and then I will speak of ideal interpolation. So interpolation, so the first interpolation you know about is this Lagrange interpolation. And so you know it in the context of, so you have a bunch of nodes, psi1 to r will be this number of nodes. And then values, and what you want is a polynomial such that at these nodes you obtain the value eta that you have decided. So here so you know this problem for where p is a polynomial in one variable. So you know that the minimal degree polynomial that satisfies these constraints is unique. So here it's kind of drawn here. I have my nodes, I have the values that I want. And because here I chose everything to be symmetric, so the nodes are symmetric according to 0, and so are the values, and what the polynomial I get is symmetric. The graph of the polynomial I get is symmetric. And now most of my talk will address the multivariate case, so where I have n variables. And so now things are a little less unique. So for instance, here I'm going my nodes, so my nodes now are points in R2 for this example, n is equal to 2. You see that they are centrally symmetric, like what I had here. And I'm going to use values eta, which are also kind of satisfy the same symmetry. But now, if I look for the polynomial of lowest degree that goes through this, whose graph goes through this red point, well, I have a lot of choice. So there is no unicity anymore. So all these polynomials, all the graph of these polynomials that you see here, they are polynomials of degree 2. And you see that this one is a parabola, so it certainly doesn't have a central symmetry. And the other one is another parabola. And only this pink one, among the one I've drawn, is pink salmon, I should say, coral, has the symmetry. Okay, so how do we get this one? And does it have more property than anything else, than the others? So I've introduced the interpolation problem we are going to look at. They are slightly more general. So here, I'm going to replace my nodes by a set of linear forms. So in this case, the linear forms are the evaluation at the points, at the nodes. But you could have some other things like the derivative and evaluation at the node. Or you could have also an integral along an interval around a domain, so you could have the coefficient of some expansion in some orthogonal basis, for instance, or things like that. So, all right. And so instead of values here, the way, and so these linear forms, I consider the linear space they generate. That will be big lambda. And hence, once I do that, I need my values to be given by a linear map, phi, which to one element in my space lambda will associate a value, r. So here, if you have, in the case of the Lagrange interpolation, if you have the evaluation at the psi i's, phi will take one of the psi I to the value eta I. Okay, so I'm spending some time on this definition of this setting, which might not be totally common, but it's not very complicated. It's just so that we have some notation. So the output is going to be a polynomial such that when we apply any of the lambdas in my space lambda, we obtain the value that is prescribed for lambda by phi. So this is the interpolation problem we are going to look at. So fairly general. So the first thing, so as I said, we don't have unicity of the interpolant, but we are going to first look for a space where you have some unicity, a space of polynomial where you have unicity. So if you have so this space, a space is an interpolation space for exactly what I said, such that for any value map, we have a unique polynomial in your space, such that you have this P interpolates your condition. So if you write things out, I mean, so you write that lambda 1 is applied to some linear combination of the basis of your space is eta 1, and then you write that for all that. So it's a linear system. And this linear system is given by a matrix, which is kind of a generalization of the van der Monde matrix. So it's also known as the collocation matrix. So it's so one row is indexed by a basis of lambda, by one element of the basis, and the columns are indexed by the polynomial in your that you're trying to check for being the basis of the interpolation space. So you have that, if you have R polynomial, they span an interpolation space if this determinant, if this matrix is non-singular. Okay, so that's fairly easy. I mean, it resembles, it's very much like in the univariate case, except we have more choices. But now this also gives you how to find an interpolation space, and particularly an interpolation space of minimum degree, meaning that, so minimum degree is what you want it to mean, is that you have, you couldn't have something with polynomial of lower degree in it. So, I mean, you have a formal definition here, but it's what it should be. So the way to do it is that you take a basis of your polynomial ring. So it's usually the monomials, and we will see it's not always a good idea. And you order them by degree, and then you form your matrix, your van der Monde matrix, and you try and you use something like a rank revealing form for this matrix. So for instance, LU decomposition of your matrix. And then you check, I mean, so you get a row echelon form for you. And so you will pick for each row, there will be one first non-zero element. And so you take the polynomial that is the column of the column, indexing the column. And that's, if you take all this polynomial, so here monomials, you get a minimal degree interpolation space. Okay. So minimal degree seems like a good idea, but as I mentioned, it's not enough. So here are the three examples of monomial interpolation space that we could obtain that way, depending on which order we put on the monomial for indexing the columns. And so you see that here you can, if your points, my points are given by this coordinate, A, B, and C, and D. So you see, I wrote down what are the conditions for this thing to be an interpolation space. So you see that it's not for any points that one interpolation space works. You have some conditions. So here you see that this condition says that the 4 points shouldn't be aligned. And so that's actually a condition for x, for both x and y to be in the basis. And then this other condition, which describes which hypersurface you stay away from, for this monomial x squared to be part of the basis. So you have kind of two hypersurface of points, of quadruplets of points, where you can't, that you can't cross for this space to work. So, and same kind of thing with the other cases. So if we operate like that on this example, so here my nodes are taken with a very nice symmetry, which is this D5 symmetry. This is the symmetry of a pentagon, or the symmetry of a pentagon. If I use this monomial basis, what I will find as interpolant is this thing. And what we want is this thing. We want this nice little star. And so that this approach of minimal degree is not satisfying. And we actually also not only want the star, so we want the quality of the interpolant, but we would also like to be able to work with, to use this symmetry to reduce the computation. And in some sense, you see that everything is given by these 5 points, 1 per orbit. And so you would want your matrices, instead of being, I think, I don't know how many points, 15, 16 points here. So the Vandermonde matrix has 16 rows. Somehow you would want your problem to cut down your problem to something with 5, 6 rows. It doesn't seem an unachievable goal. So this was interpolation, and let me introduce this least interpolation space that is in the work of De Boer and Ron.
Well, to your last slide, so what you really want to say is you prefer compact surfaces, because the other surface also had all the symmetries, right?
Which other surface?
You had 2 surfaces. No, the next slide. And so the left-hand side, okay, the left-hand side doesn't have the correct symmetry. So how do you say which one you actually want to get?
I want the one with the D5 symmetry.
Okay, so the left-hand side here doesn't.
I want it to be invariant under the action of D5. Yes, thanks for pointing out the little lack of precision, maybe. Yeah. I mean, you can see that this doesn't have a D5 symmetry. I mean, you have it's totally different. All right. Okay. So I need to introduce a bunch of things, but yeah. So our space lambda, it's a space of forms, and this the dual of the polynomial ring. So that's the set of linear forms on the polynomial ring. So you can actually, it's isomorphic to the formal power series ring. And so the way to see it is that, so I'm going to write this power series in the partial operator to make it very explicit what it is. So if you have a power series in the, it's basically a differential operator. So the way that you apply, so if you have a series in these partials, and then a polynomial with the coefficient p alpha, coefficient f alpha, if you apply this, the linear form that is underlying this f to p, I mean, it's just applying the operation and evaluating at 0. Okay. So you have the duality. So for instance, if you write it, so if you have a lambda, you know, on the monomials, you can write your power series like that. If you want to take the evaluation at a node psi, the power series that corresponds to it is the power series of the exponential of the dot product of psi with the partial dx, dy, etc. So this kind of duality is kind of, I mean, this thing is kind of interesting. So now if you think of your lambda that give you your interpolation problem as power series, and then you take all the lowest degree terms. So by that, so if your lambda is written with partial degree 3 and then partial 4 and higher degree, you just keep the low degree and make it a polynomial. So you take, so the lowest degree terms are this lambda down a row, and I'm taking all of them, but for a lambda running through a big lambda from all my interpolation condition, then this is my interpolation space. It's an interpolation space, and it has some kind of very intrinsic things. So this was defined in these papers that I said. I mean, and to me, this definition was super mysterious. I really kept, I mean, I understood, but it was kind of a very intrinsic thing. It's only when I looked at this interpretation with ideas and H bases that we will see at the very end that it really started to make sense. But it's kind of a very intriguing notion, I thought. So so the next thing we want to do, I mean, is how to compute this interpolation space that has good properties. And for that, I'm going to introduce this apolar product, so which stems from the pairing between the dual vector space, the dual to the polynomial ring, seen as a formal power series, and the polynomial ring. So you have the apolar product between two polynomials p and q. You take p, make it a differential operator, and apply it to q. So if you write it, if your p alpha and q alpha are the coefficient in the monomial basis, this is how you write it with this alpha. So this is actually a very natural scalar product for polynomial. It comes from very different angle. It comes to that. So you're going to define the dual of a basis. I mean, if you have a set of polynomials that span, I mean, that is the basis of your polynomial ring, the dual polynomial set will be also a basis with the property that you have this orthogonality condition at each step. Okay. So, for instance, if you start with the monomials, the orthogonal basis is this 1 over alpha factorial times x alpha. So it's and everything that Ron and De Boer wrote was in these two bases. So I mean, they didn't. They really worked on those bases. But now, if you want to work with other bases, like we are going to see, and you want to express your lambda as a power series in some other basis, then this is how it's got done. So we saw it for the monomial basis, and this is for any other basis if you write it in terms of p and p alpha dagger. All right. So this gives us actually the solution on how to compute it. It's again, we start again from this Vandermonde matrix. We do another LU decomposition. But this time, so from the row echelon form, we don't keep only the polynomial in the row where the index is, the non-zero element is. We take all this part, all this homogeneous part of your polynomial. We take all this homogeneous part, but since it belongs to a certain lambda, you have to understand it with the dagger. So that's if you take this coefficient with in your basis in your dual basis, you obtain exactly the list, a basis for the least interpolation space. All right, so now the example we've seen before. So we see here that this were the example we got with the monomial basis. And this is the interpolant we get if we apply this least interpolation space. And you can see here that it nicely has the symmetry of the central symmetry that was already with the points. So this other monomial interpolant was also with this symmetry. And this one has an additional property that it has, we saw that this was a valid interpolation space outside of two hypersurface. And here we can see, I mean, so this is the interpolant. I mean, no, this is part of the interpolation space. But this interpolation space now is valid for slightly bigger space. So because what you have to avoid is not an hypersurface, but a much smaller kind of set, lower dimension set. So it has a, and this, so I'm going to call on your memory, I mean, for those who were there, in this talk, in the introductory workshop, I mean, this is a property that was used, that you could really collapse things and have them actually tend towards some derivative condition. Stop me if I'm wrong. Okay, so this was, so this you've already seen it, maybe without your knowing, but it was there. All right, so this was the, so this is, so this least interpolation space has the symmetry, but so far we haven't, so it will preserve the symmetry, but we haven't used the symmetry to make it, to make the computation smaller. So that's the next step. And also, if we are using this approach, I mean, we have to deal with the big matrices, and so if you do some LU, you might accumulate some errors, and in the end, you might, so the theoretical least interpolation space will have the symmetry, but the numerical might have lost them substantially. So we want to kind of correct that, keep the symmetry despite the numerical, some possible numerical accumulation of errors. So this is what we're doing, this is where the contribution is. So what is symmetry here? I mean, you probably know better than I. And so this is, this will be given by a finite group in this talk. And it's a finite group with an action on the space Rn that is linear. So it's given by a representation that is a morphism from your group to the group of matrices in Rn, of a general group. So we are speaking of reflection. So we've seen some reflection symmetry for the pentagon, but here this is another type of symmetry. All the symmetries of the triangle, it's given by reflection and rotations. And here you can see some other reflection symmetry, but now where it's not an orthogonal reflection. And here it's simply given by rotations. Okay, a rotation by 2 pi over 3. So those are the type of symmetry we can consider, and probably more. So if you have a representation of Rn that induces a representation on the polynomial ring, and the action that will be given by a rho. So rho is my representation on the polynomial ring, and rho star is the representation on the dual. Okay? And so you define them for, so the action G acts on P by composing P with G minus 1. And here you have to put another minus 1 somewhere. So it's a bit technical, but so what we want is to use this symmetry to kind of put the problem in the end in a block diagonal form, to put the Vandermonde matrix in a block diagonal form. And this will be possible if we introduce this, we use what is known as symmetry adapted bases. So let me go through this type of construction. So the first thing to know is that if you have a finite group, there are only a finite number of inequivalent irreducible representation. So irreducible representation means that there is no invariant subspace. So you really have it all. So now you have this invariant, this irreducible representation, n of them. So if you have another representation, like on the polynomial ring or its dual, then you can write it as a sum of irreducibles. So there will be C1 of the first one and C2 of the second one, etc. Okay. So we will. So you can decompose your space V into n pieces, and each piece is n copy is the Ci. The ith piece is Ci copy of the if irreducible representation. So it's written there, and these Vi are Ci time the irreducible representation, which is of dimension Ni. It's all notation. So the symmetry adapted basis will obviously kind of satisfy this partition, and it will be defined, or its property will be that the representation of your group in this basis, the matrix of a representation, are going to be block diagonal, and each piece is this irreducible representation repeated a number of times, Ci time, but then in some kind of fancy way. All right? So this is the property we're going to use. It decomposes in blocks. And then I should add that there is a standard, very classical way of computing this symmetry adapted basis. These spaces are given this space and this space. They are given explicitly by projection. They are given by projection, which can be made, which are explicit in the terms if we know the irreducible representation. So this is all kind of very well explained in the book by Serre, which is reasonably elementary and a lot of fun to read, actually. And so this is kind of standard. There are more interesting way of computing, or more efficient, more interesting way of computing this symmetry adapted basis in some cases, and we're also working on figuring it out also without knowing the irreducible representation. So now, I mean, the emphasis so far was on this Van der Monde matrix. But what is behind this matrix is a linear map. It's a linear map from your polynomial ring to the dual of lambda. To a polynomial, you add this pairing, this pair, but to a lambda will associate a value applied to P. Okay, so this is this map. And this map is equivariant, meaning that you have this kind of commutation of W and the representation. And so when this happens, this is where the power of the symmetry adapted basis comes around. You can write the matrix of your map in a symmetry adapted basis. It does block diagonalize. So I could have written that way. You can write it, these diagonal blocks are here, but I'm spelling them out here. So for each irreducible representation, you have one block, and within this block, it's again block diagonal with the same block repeated many times. And it's repeated the dimension of your representation. And the size of this block is the multiplicity of the representation in your space. Okay, so that's what's happening. So you see that what we have to do some decompositions of LU decomposition. So we can do it only on this block. And to do it on this block, we actually only need to do it in one block and repeat the operation in the others. So example of symmetry adapted bases and some block diagonalization of Van der Monde matrices. So here I'm going to look at the symmetry of a triangle. So those are made of rotation, 3 of them, and reflection, 3 of them. And if I look at the symmetry adapted bases of the polynomials up to degree 3, what do I get? I get a first component that corresponds to the trivial representation. So this first component are the invariants. So you see that you have the constant, polynomial of degree 2, polynomial of degree 3. Now this piece corresponds to the skew symmetric representation by the determinant. And this one corresponds to the dimension 2 representation, which is exactly this one. So you see that it has 2 blocks, and each block has two elements. So this size here, it's the multiplicity, and the number of blocks is the dimension of the representation. All right, so now if we take points, so my points, so if I take my points to be in an orbit, my nodes to be in an orbit, so that's 6 points here. I'm taking these 6 points. So I have evaluation at this psi I. And now with this evaluation, these maps, I can compute also a symmetry adapted basis. So this is here something that corresponds to the invariance, so the trivial representation, the skew symmetric representation, and the 2-dimensional representation. Okay, and I write now my Van der Monde matrix in this 2 bases, and boom, it's block diagonal. And the blocks are written here, and you see that you have twice the same block. Okay. So this was, the previous example was the typical case of a Lagrange interpolation with symmetry. And here we could also have done a case of Birkhoff interpolation. So it's not the evaluation at the nodes that we want, but let's say that our linear forms are derivative, radial derivative, and composed with evaluation afterwards. So those are my this rho I type of linear form, but the decomposition is the same. The decomposition, the linear, is the symmetry adapted basis for lambda is same shape, and we also have a block diagonalization. All right. So now, so to obtain this, so to obtain a minimal degree or least interpolation basis of a minimal degree interpolation space or basis of a least interpolation space, it's very much like before, except that we apply it to each block. We don't need to repeat the operation in several the repeated block. So we do the LU decomposition, look at the index sequence, and repeat the same thing in each block. And this is, and then we get so either a minimal degree or least interpolation space by repeating this operation. So, okay, what do we get? So this, as I said, so M is of minimal degree, but it's also an invariant subspace. And the M we computed is a symmetry adapted basis. Now H is a basis of least interpolation space, which is, we knew it already invariant. But now H is a symmetry adapted basis, so it has this block diagonal form. So what we get out of this part is that if we use this symmetry adapted basis as basis for the interpolation space, we are cutting the problem in little pieces. So if you can choose your nodes and you choose them with a certain symmetry, there is always of cutting down your problem.
Well, your first point there, does it mean you're saying it's of minimal degree? It's of minimal degree among all spaces that have the symmetry, or it is of minimal degree within all polynomial interpolation spaces?
Within all polynomials. It is among all polynomial, but it is invariant.
So you never have a degree raise because you enforce symmetry?
No, no. All right. Okay, so we have cut the problem. We have cut the problem independently of whether or not the values, this function phi, has some invariance or some symmetry. So it's for any data. So now what happens if we have this value? I mean, if we have actually an invariant interpolation problem first, and then we'll do equivariant afterwards. So what is an invariant Lagrange interpolation problem? So my nodes are arranged into orbits. My values satisfy that for any points on the orbit, I want the same value. So what did I write? So now if I have so more generally, if I have an interpolation problem that is both given by this space lambda and a phi, I will have this will be an invariant problem if lambda is invariant, but also if you have this phi that satisfies the natural condition that for 2 points, two linear forms which are in the same orbit, you get the same value. Okay. And so what you, the property here is that if you choose an interpolation space for your lambda that is invariant, and your phi has some this invariant property, then the interpolant you will get is invariant. It just takes lambda to be invariant. Okay, so this is so if you choose lambda to be what we computed before, minimal degree or least interpolation space, you obtain this. You will obtain this nice little this nice star. So now equivariance. So now we are interpolating not one function but a vector of function. So that means we are interpolating each component, but that the fact that we have a polynomial map lets us define what is equivariant. So we, on the space Rm, Rn, so we have, as before, this theta thing, and for on our mth dimension space, we have this other theta. And so again, like we have already seen in equivariance, if we can kind of commute the action and the map F. So now my interpolation problem is equivariant if I have the same equivariance at the level of my value map phi. Okay? And the result is actually kind of the same now. If lambda is an invariant space, if interpolation space we choose for lambda is invariant, then and you have data which are equivariant, then your interpolant is going to be equivariant with the same equivariance as phi. So that's what it is. So I'm going to give you some nice example that should help with the concept and seeing why it could be useful. So here I'm trying to create a vector field that will be equivariant. So I decide, the way I'm going to decide that is I'm going to take at the vector field, I want the vector field, so at this point and this point, to be given by this little arrow that I did draw. Okay. So that means that I want a map from R2 to R2, so a point in R2 to a vector that is, so I want this type of map that is equivariant and that will interpolate these two vectors and has the good symmetry. Okay, so that's I applied what I did before, and here are the integral curve of the polynomial field that I can compute. Okay, so let me start again. I have these vectors in the space at 2 points. So those are maps, and I want a map, a polynomial map from R2 to R2 that is equivariant. So these are two components, two polynomials that I will obtain with the, by setting up my problem, finding an interpolation space that is invariant, and taking this initial condition, and voila. Another example is if I want to have a symmetric parametrization of a surface. So again, I have a map that here that goes from R2 to R3. On R2, I'm going to have the symmetry of a triangle. And on R3, I'm going to take the permutation representation of D3, which is the same as S3. And so the image here of those lines that you see here, I will find them on this map. So you see that the symmetry is nice. And my interpolation condition, we have this Birkhoff condition that I wanted at these points the derivative to be exactly a certain value. And so those are these vectors. Okay, so those are illustration of the equivariant interpolation. All right, so conclusion of this part of the talk. What is coming after that? And what time is it? Sorry, I'm a little confused. It's what? 46. Oh, perfect. So I will conclude first by saying, you know, what are the benefits of using symmetry-adapted bases? So the first thing is that if your lambda, so if your nodes have symmetry, then you're block diagonalizing the Vandermonde matrix. Okay. Now, if your problem, if you have this interpolation, if you have already this nice invariant interpolation space, without you knowing explicitly what is the equivariance satisfied by your value map, phi, the result, the interpolants, are going to satisfy the same equivariance. But numerically, it might not if you're not using this symmetry-adapted basis. If you do use this symmetry-adapted basis, even if the numerics gets wrong a little bit around the computation, the output will still have the symmetry, the good equivariance. So that's kind of a, and sometimes, you know, qualitatively, it's more important to have the symmetry right than to have the numerics completely right. So that's kind of this, this is kind of a take-home message of this talk. And, and I was going to go a little bit through the next step that we haven't finished. It's still work in progress, where we are doing ideal interpolation. So ideal refers to ideal in a polynomial ring, not to idealism. So this is kind of a sort of motivating example. So now, you know, you can see these interpolation points, which are kind of taken with the symmetry of the cube in different places. And so what we want here is to find the function f. So far we have looked at the interpolant like that interpolate graph of function that interpolate points. Here we want to find a polynomial f such that the zero set of this polynomial goes through this point, and there might have some here you have some tangency condition on the right on the green points. So finding an algebraic surface that goes through a certain number of points with some tangency conditions. So that you can't really do with this interpolation technique, since all your conditions are 0, 0, 0, 0. And so if you fix an interpolation space, the only polynomial that will be 0 everywhere will be 0. So you're not getting that. So what you want is not the interpolation space, but the kernel of all those lambdas. And so this is ideal interpolation refers to the fact that if you take the orthogonal of your lambda, so that is the polynomials which are killed by all the lambda in your space, then this orthogonal is an ideal. So you can think of it as a generalization of Hermite interpolation, where Hermite interpolation is when you want to fix some derivative to a univariate interpolation problem. But you can't have roles. If you have a third order of derivative, you also need the second, the first, and the evaluation. Okay, so ideal interpolation is a bit of a multivariate generalization of that. So, and here the goal in this situation would be to compute simultaneously a symmetry adapted, a basis of interpolation space, and what was done before a Grobner basis of the ideal. And here, Grobner bases are known to not work with symmetries. So we would like to use another less used concept, but earlier concept, the concept of H basis, to kind of work this out. So why do we want to do that? Why these people were kind of interesting? So there is a really long list of working with Grobner bases on this problem. It has, so first it was used, it's important in the design of experiments to find the relationship, algebraic relationship that are satisfied by a set of nodes. It's also, starting with this paper, probably, if you want to, your set lambda could be associated to normal form via an ideal that could be given by a Grobner basis according to a certain term order. And you want the Grobner basis according to another term order. And so if that's where you choose your lambda to be these normal forms. And also there is another whole set of problems like cubature, sparse interpolation, error correcting codes, and tensor decomposition that are somewhat related to this problem too. And this is through the use of a lambda, which is generated by a single linear form. That is a combination of a linear form of evaluation, and where you know the value of this omega on monomials, but you want to refine these nodes, and this is declined in these different approaches. So this is the next step, and I had some slides to kind of give an idea of how we are going around to do that, but this is rather. I'm very happy to let that, to speak about it to people who are more interested and have some background in Grobner bases. And I'm finishing with pretty pictures. Say that again, sorry?
Your equivariant dynamical systems, there was more than one. So would you expect, do you get a complete set, or maybe I just didn't understand the slide.
So you mean they are not unique?
Well, you had two pictures.
Oh yeah, but they are not, yes, sorry. So this might have been computed. So here my vectors are kind of going, so the vectors by my values, my initial conditions, kind of, my interpolation values, they are not the same on these two examples. So you see that on this one, you're kind of going away from. I have a central point, and I'm trying to go away. So it's I will have a limit cycle, and here on this other thing, I'm kind of going concentrate. I'm going towards a point, and so you have this terrible equilibrium point that is happening. So these are two different equivariant dynamical systems. No, yeah, okay, I'll make the arrows bigger. Thank you. Yes. Getting your point. All right, very good.
You said at the beginning that the lambda down arrow, which I also found mysterious when I was studying this, became more obvious when you were doing the symmetry adaptive?
No. It's when I'm doing the ideal interpolation.
Yes.
Because so it's so I'm just going to give you the final point. So if you take the set of, you have your ideal, and you take the set of all the initial forms, so the highest degree part of the polynomials that are in the ideal, and you take the orthogonal complement of this thing, then this is your least interpolation space. So that's, you know, because we are trained with this initial ideal, etc. To me, it makes more sense. Yes. Very good point. Very good point. So in this ideal interpolation, where we will compute, you can. So I explained with the LU. You can use also some other rank revealing forms like QR. So you can use QR decomposition as well, or SVD. But then you have to do it degree by degree. So the interesting part of this LU is that I could do it in one go with putting all the degree. But if you do it with this other method, you have to do it degree by degree, and so it's the algorithm becomes a bit more involved. Yeah, the idea is that that would be more reliable.
So if you calculate this H basis, so if you calculate all these polynomials whose common level set has the symmetry and interpolates your point, and you compare that with not enforcing the symmetry and using a Gribner basis, do you have a range in degree, the polynomials that we calculate? Or
For the H and the compared to the Grobner basis?
Yeah.
No. I mean, it would be more like the H basis should, if anything, should be of lower degree.